So we're doing a policy gradient, and just to remind you, the idea here was that value functions maybe tell you more than what you need to know, right, to take action. So they tell you a Q function tells you the exact value of every action, but when we use a Q function to actually act in the world, we just want to know which action has the highest Q value. And so you don't need to necessarily have all that value information. And policy gradient or policy search techniques are saying, okay, yeah, let's just try to directly search for a good policy without learning a value function. We'll see that sometimes to do that, it will actually be useful to learn some types of value functions, but the main focus is on directly manipulating the policy parameters to find a good policy. And we also, this is another good motivation for this, is when you come across a domain where the number of actions is very, very large or even infinite. And so far, everything you've done, for example, value iteration, if you had an exponential number of actions, right, that maximizing step is going to take a long time, right? And right, so you always have to max over actions in all of these algorithms, Q-learning, value iteration. And so that max operation, if it's continuous values, you're going to have to do it analytically or numerically, and it can be problematic. And so if you're doing a policy search approach, you can just have a policy that directly outputs the motor torques, for example, if we're talking about a robotics application. So this would be a vector in Rn, and you don't have to do any maximization. If you can learn that policy directly, you just directly compute it. And so that's a nice that's one nice aspect of this compared to learning a Q function. So not to say that you can't learn Q functions in domains like this, it's just there's a lot more that you have to pay attention to. So for example, I've seen people do work where they'll learn Q functions that are convex in the action variables. So they force the form of the Q function to be such that what you learn is a convex function in terms of the action variables, and then you can use convex optimization to find the optimal action. And you can play games like that, but it's a lot more hassle. So we said basically we're just going to do gradient descent in the policy space. And let's find a nice slide for that. Right, so here's our parameters for the policy. Might be a neural network. And we're just going to try to estimate this. And remember rho here, let's just remember what this was. Rho is what we're using to represent the basic value of this policy. And in this part of the course, we're basically assuming the policy always starts in some initial state. And the value of the policy is just if you run it for a long, many runs, many episodes from this initial state, what's the average value that you get? So the expected value of running it from the initial state. So is it you clear what rho is? So it's like a value function, but we're not indexing it by the state because we're just saying it's the value of the initial state, like the value of the initial game state. And rho theta is what we're going to use for that. That's what we want to maximize. And so we want to maximize, when we change the policy parameters, that value changes, and this would be how you do gradient descent. And the whole problem is this is not a nice functional form. This is not a polynomial. It's not any nice analytic form. It's a messy expectation with lots of nesting, and you're not going to be able to do this analytically. And so we're going to somehow figure out how to use experience of running the policy to estimate the gradient, then take a gradient step, then use experience of that new policy to estimate the gradient and take a gradient step. And that's what policy gradient algorithms do. So one thing we talked about last time was if you have a deterministic policy class, you can end up having discontinuous value functions, right? Because Tiny change to the parameters can cause the policy to change deterministically, and that can change the value. And so you can end up with situations like this, which we went over last time. And so we said typically what you'll see when people are doing policy gradient is they're going to use probabilistic policies that are policies that return for a state a distribution over the action, so probability distribution. So if you're familiar with things like softmax from neural networks, and this is softmax, this will give you a score for every action, and the score is summed to 1. So that's a probability distribution. So the nice thing about that is when you change the parameters, you just make, a tiny change to the parameter makes a tiny change to the probabilities. And so you kind of smoothly can vary the policy. All right. Now, you can imagine that there are some issues with using probabilistic policies, like in domains where you can fall off a cliff. If there's a non-zero probability of jumping off the cliff, even if it's very small, that's kind of an unfortunate thing to be using a probabilistic policy for. But yeah, a lot of times, so that will actually cause challenges in a lot of learning problems, and we'll talk about that as we move on. But this is a very common thing to do, and typically what people are hoping is that the probabilistic policy just keeps getting more and more and more deterministic as you learn, and eventually the probability of doing something stupid just goes to 0 essentially. And so that's what they're banking on, but sometimes it's hard to get off the ground to get to that point because you just keep jumping off cliffs and you can't ever do anything besides that. All right, so then we said, then we talked about what is the most straightforward approach to estimating a gradient of a policy. And this is a picture of that approach. So let's say your policy has 3 parameters, theta 1, theta 2, theta 3. Well, what could you do? You could say, I'm going to first estimate the value, I'm going to run trajectories with the original parameter values, like this is my current policy. So you run n trajectories here. Then I'm going to tweak my first parameter by epsilon. And now I'm going to run that new policy, right? So I change the parameter a little bit. I run the policy, and now either the average of these, right, the value you get from these will be a little better than this or a little worse than this, right? If it's a little better, well, you probably want to move in that direction, move theta 1 in that direction. Same thing here. You change the third value a little bit, and you see whether things get better or worse, okay? So this is called empirical gradient estimation. That's the fancy name for it. And basically you're just tweaking parameters, and if tweaking it improves performance, you change the parameter in that direction. If it makes things worse, you change the parameter in the opposite direction. So that's what you would do if you didn't know calculus, or you were just doing this on your own, trying to come up with the fastest way of trying to optimize parameters, right? So the problem with this is that you have to do a lot of runs of the policy, right? So if you imagine, the biggest time consumption for these algorithms is the time to execute trajectories, right? That's what you're really that's what the real cost is in reinforcement learning. This is pretty expensive, right? Especially if you have a lot of parameters, because the number of trajectories that we have to run here scales with the number of parameters. And so if you are going to try to do this with a neural network with 1 million parameters, yeah, good luck, right? You're not going to want to do it that way. So we need some other mechanism of computing gradients that is not just this tweak and test approach. So that's what we're going to talk about now, and we'll get some ways into that during this lecture. And so, yeah, what we're going to do, and these words are really for you at home, this empirical gradient approach, the problem with it is it did not care that we were actually running policies or that we had an MDP, right? We just changed the parameter and we called a black box that gave us numbers back. And it did not try to exploit any structure in that black box. And what do we know about this black box? Well, we know it's a Markov decision process. We also know the form of the policy, right? It's a parameterized policy, and we know it. And we should be able to exploit that information to be able to do better than what we just talked about, where you have to run so many trajectories. And in particular, what we want to do is, it would be really nice if we've got our current policy with the current parameters, and what if we could just run that policy multiple times, just that one policy, as opposed to all of these, we'll call them tweaked policies. If you could just run these and estimate the gradient from that, right, just from these trials. So that's what we're going to try to do now. We're going to show how to do that. So you've got your current policy. You just run it a few times, maybe 100 times, maybe 10 times. You estimate your gradient just from those trajectories. And that's the idea behind a typical policy gradient algorithm. So let's see how we can do that. Basically, all of these algorithms, almost all policy gradient algorithms, are based on something called the policy gradient theorem. And the particular algorithms are just different ways of approximating parts of the policy gradient theorem. Okay, so we're going to start out by showing the policy gradient theorem and getting some intuition about it. And then we'll derive a series of algorithms that are out there. But once you understand these things, you'll be able to pick up a lot of the papers, and you'll see, oh yeah, they're approximating this part with this, and it's just, so many variations you can't even count. But that's what most of the papers are doing, different variations of the policy gradient theorem. So let's think about the challenges here. So let's think about what this gradient is. So this is the gradient of the value of the policy when we have parameters theta. Right? So it's sort of saying, if I change the parameters a little bit, how much is the value going to change? And it feels like, that gradient is going to be impacted by a couple of factors, right? And I've listed them here. So one is, when you change the parameters, it changes the distribution of actions, right? And so that's, right, because that's what the parameters are adjusting, the probability of taking each action. So that's obviously something that's going to affect the value of the policy, because in one state, you might get a big reward for one action versus another, and adjusting towards the big action will give you a bigger value. But the other thing that changes, which is more complicated, is when you change these parameters, right, it changes the whole distribution of states that you might encounter. So if you think about supervised learning, where you just have a set of data and you're just trying to learn to pick classes for the data or pick actions for each individual data point, this is the only thing that you really have to worry about. But in reinforcement learning, when you change your policy parameters, the whole policy can go through different parts of the state space. It can go to good parts of the state space now, maybe, or it could go to worse parts. And that's actually the thing that's really hard to get your hands around analytically, right? Because that's a very complicated dynamic system that has nested sequences of equations. And so this is really the hard part about computing the policy gradient. The first part is pretty standard, and if our state distribution did not change, this would be a pretty easy problem. Okay? So, yeah, that's what these words say. So the interesting thing, so if you think about that more, and this kind of worries you, the policy gradient theorem is pretty amazing in some sense, because it says that you don't actually have to account for the change in distribution of the policy when you tweak parameters to get the policy gradient. So that's sort of the main power of this policy gradient theorem. And so all you have to know is the state distribution of the current policy. We can get our hands on the distribution of the current policy because we can just run it, right? Empirically, we can just run our policy, and that's all you need to know. So let's see if we can make that make sense to you by showing the theorem. So this is a theorem. I'm not going to prove it. It's a pretty short proof in Sutton and Barrow, the book that you have. So let's look at this for a bit. So this of course you have to assume that the policy is differentiable. So this is a stochastic policy that's differentiable in terms of theta. And so this is what we're after, right? And the policy gradient theorem tells you exactly what this is in terms of a couple of things here. So let's try to break this apart. So this is an expectation. And what's an expectation over? It's an expectation over the random variables here are S and A. So S is a state and A is an action. And these random variables are distributed according to, if you run the policy over and over and over, what's the distribution of states and actions that you see, right? So it's an expectation of the state-action pairs that you see when you run the policy. Does that make sense? So that's what those random variables are. And this is just how we denote what the expectation is. And this is with the current policy. We're trying to compute the gradient of the current policy. This term is called the score function, and you'll see this all over the place in many different areas, but in machine learning, this comes up all over the place. Basically, what is this? So this is our policy, right? So this is giving the probability of taking action A and state S. That's what this pi theta term is saying. Log is just a monotonic transform, so it doesn't really do anything but squash things. So bigger probabilities will still have bigger log probabilities, right? And this is the gradient of this thing, and this is going to be a vector, right? So this is theta is a multidimensional vector in general. It's going to be a vector that points in the direction that will cause you to increase the probability of taking action A in state S, right? So think about what this is again. This is a vector that if you look at a particular state and a particular action, it says which direction can I change the parameter theta to increase the probability of taking that action in that state, right? So that's all the score function is. And intuitively, if you thought that taking state action A in state S was good, like it was really good, you would want to move in that direction, right? You want to move in the direction of the score function. If you think that taking action A in state S is really bad, you would want to move in the opposite direction, because that would decrease the probability of taking A in S, right? So it's very important that you understand what this is. It's a vector pointing in the direction of increasing the probability of A in S. And so finally, we know what this is. We've already learned about the Q function. So the Q function is just the Q function of the policy. So if I take A in S and then follow the policy thereafter, what's my expected value, right? And so all of these things together, if you take the expected value of these terms, gives you the policy gradient. And we can now dig in a little more and try to interpret it some more. So that's what we're doing here. So I'm not sure how obvious it is, but this expectation, if you want to think of it as a big sum, you could think of it as a big sum. At the end of the day, it's going to be a big sum over all the SA pairs that are weighted according to their probabilities of occurring. But each term in that expectation is going to look like this, right? Where S and A are concrete particular actions, right? These are random variables up here because it's inside the expectation. These are concrete actions. And so each of these terms is a vector, right? And it's a vector that points in the direction of increasing the probability of A and S, weighted by the Q value of A and S, right? So actions that have higher Q values are ones that we tend to like, right? So if you think about what do we do in policy iteration? In policy iteration, if you start with pi prime, right, you compute the Q function, and the maximizing action of that Q function is the improved policy, right? And so this is basically saying, well, if if the action is large, we're going to try to move in that direction more. So this actually makes a lot of sense, right? Policy iteration, the extreme case, you would find the maximizing action, and you would move the parameters in the way that sort of completely maximizes the probability of taking that action. Here, we're not going to be able to do that. We're going to take a little step in that direction. So at the end of the day, the policy gradient here is a combination of these terms for every state action pair. And the directions, the gradient directions that have higher Q values are going to be weighted more. And so you're going to be pointing in that direction more for the overall gradient. Okay? So there's a lot of words that can explain this at home if you didn't quite get that, but ultimately that's all that's being done here. What directions improve the probability of certain actions, and we're going to weight those directions by how good we think they are based on the Q function, and the linear combination of those is where we're going to move our parameters next. All right. So any questions about that you could formulate? All right. So next time we're going to basically see, so we can compute this, right? We're usually going to have a closed form. We're going to have a parametric form for the policy. That would be a neural network, for example, or a linear function. So we'll know this. So we can compute this thing analytically, the score function. The part that we don't have, I mean, it would be really nice if somebody just handed us the Q function for the current policy. We don't have that. And so the different algorithms for policy gradient will try to estimate this Q function in different ways. The first one we show, which is called reinforce, which was invented way back in the early 90s, they use Monte Carlo estimation for the Q function. We'll see another approach that will use TD estimation for the Q function. So from here on, it's going to be kind of a standard story that we've already seen. It's just different ways of estimating this term. And there'll be some extra things that you haven't seen to sort of decrease the variance of these estimates, but we'll get to those as we come to them.